This is lecture 10 that is supposed to be conducted this coming Thursday. So I'm going to talk about uh, fatigue of materials. Now, we did talk about the effect of transition temperature on the mechanical properties and the behavior as well as the service life of materials, especially metals. So now we are going to talk about one of the most important service parameters in materials, that is fatigue. What is fatigue? Fatigue is repeated application of stress. So you can think about engine components or something like repeated bending of components like paperclip or aircraft wings, etc., etc. So it is an application of uh, cyclic stresses and strains. Now, when a component fails due to fatigue, what is it that you see? Especially in this case, this is a keyway of a bolt. Uh, so you can see that it is generally flat. There is not a whole lot of plastic deformation. So because if there is plastic deformation, what happens to an advancing crack? It gets stopped. So if there is no plastic deformation, then you can kind of assume that it the failure occurred due to fatigue. Now you can also see um, the type of markings on the surface, and these markings have specific names on them. They are either called beach marks or striations or clamshell markings. So these are, and each of these are due to the crack extension, and each of them is a ratchet line, or each of them is a ratchet line, and it is due to the extension of that crack at a specific stress level. So you can see that. So think of being on the beach. So these are called the striations or beach markings. So if you see that kind of a marking on the surface of a component, of the fracture surface of a component, you can assume, very safely assume, that it is due to fatigue failure. Now, uh, you can also have some featureless type of uh, surface markings, but sometimes you will see that there is some kind of a discoloration starting from one corner, one very weak corner, and these lines are kind of radiating out. And especially if your component is going to be experiencing constant constant stress, you can safely assume that the failure has occurred due to fatigue. Okay, now how do you represent that in and for engineering design applications? So you plot the cycles to failure versus the applied stress levels, and you determine the cycles to failure for each stress level, and you plot that. Now if you see this kind of a, this is called a hockey stick. If you see that kind of a behavior, it is typically seen in the case of BCC type of structures. Now if you have FCC and very plastic type of materials, this hockey stick will not be a very sharp change um, in the failure mode, but what you will see is that it is a gradual reduction in um, the not reduction, gradual increase in the number of cycles to failure as a function of stress. So what is typical here? The higher the stress that you apply, the more easily the component will fail. Okay, so you can see that if you applied 800, um, so this one they call it centness. So think of it this way: 800 ksi. Okay, if you applied 800 ksi, it only withstood something like 2 into 10 to the power 4. But suppose you reduce the stress to say um, 8 into 10 to the power 4, then no, I'm sorry. If you reduce the stress to say 700, then it can last up to 8 into 10 to the power 4. If you reduce it to 400 ksi, then you may not even find any stress at all. Now, you can also have the effect of notching and sharp um, stress concentrations that you can see in the case of the fatigue failure. So if there is no notch and there are no sharp stress concentrations, that means the component can withstand much higher stresses for the same number of cycles to failure. So if you have a notch versus unnotched from this sample, what can you say for the same stress level? Okay, so if you have an unnotched sample and you applied say 500 ksi, that means the notched sample will only last for say something like 5 into 10 to the power 4. But suppose you had no notches, then how many cycles can it withstand? Probably unlimited life. So the effect of the notch and the sharp stress concentrations can be pretty substantial. So please understand that, okay? And so what can you say about fatigue? Fatigue is typically a three-stage process. First, the uh, crack initiates, then it propagates, and then the sample cross section can no longer take that load and it will fail catastrophically. So typically it will initiate. So depending upon the stress, suppose you applied a lower stress, then it can withstand much higher number of cycles. But suppose you had a higher stress, then it will fail much faster. Okay, so um, now Ni is for initiation, P is for propagation. So once the crack has initiated, typically the number of cycles for propagation will be less than so in this case it might be less for initiation than propagation, but typically for most components, most materials, what you will find is that um, higher the stress, faster will be the initiation and faster will be the propagation. So you can see that the material will fail as per the stress concentrations. So suppose you had um, a very gradual cross-sectional change. That means it has less low stress concentration and a large fillet. So which means that when the sample has failed, the failure is, um, you can see that in some areas there will be, you will find that the failure is, the fatigue is concentrated in that area. So you can see that those beach markings and striations are concentrated in the area where there is high stress. Okay, so typically what I want you to take away from this is that if there is high stress concentration, the sample will fail at a much lower number of after a much lower number of cycles. So how do you test it typically? Um, these are done by, I don't know if we have a um, lab for fatigue failure or not. I wish we had one, but if not, we might be. Um, I think I have to ask the TA if we have a lab on fatigue failure or not. So typically, what they do is you have a circular sample, and then you have um, some kind of a pulley on which you apply this load, and this keeps rotating, and after a certain number of cycles this sample will break, and it will tell you what is the number of cycles versus the applied stress. You can also do a modification to that. So you apply um, two loads, one on each end, and you keep rotating in the same direction. So the same way you can do the fatigue failure versus number of fatigue stress versus number of cycles. Or what you might do is you have a hydraulic testing machine, and you have a sample, and you put it in between these two grips, and you apply maximum stress and a minimum stress, and then um, you keep applying this stress between, you keep um, going back and forth between this high stress and this low stress, and then you see the number of cycles after which you have the failure. So you have a maximum and you have a minimum stress. So that is used to create the median stress. So the median stress is the maximum plus minimum by 2, and the delta stress is equal to maximum minus minimum, or you have an average, um, which is no, this is the average, and this would be the amplitude, and that would be the maximum minus minimum by 2. Or you might also have a ratio of the minimum over the maximum. So sometimes you might have a ratio of zero point 0.1 and things like that. So these are some of the parameters that you would use for determining the fatigue life. So typically when you plot the number of cycles versus the nominal stress, that nominal stress can be based on any of these parameters. Okay, so and then you would plot the parameters accordingly. Okay, and so typically what you might find is that um, you would apply this for the median stress level, and especially at lower stress levels, what you will find is that there is a significant scatter and smaller scatter at high stresses. So this tells you that you have to consider statistical variation in design. So what is the effect of stress? As I said to you, when you apply a higher mean stress, the fatigue life decreases. Okay. Now, if you applied a lower mean stress, it will last for almost indefinite life. It can last for indefinite life. So, what you are seeing is that fatigue failure is a cyclic stress control fatigue, cyclic stress control failure, and you can control that depending upon the. So, if you look at the handbooks, it will tell you what is the safe stress at which you can use these components and get you the safe life. So if you applied a stress level um, below this mean stress level, it can last forever. Okay, so in this case, sigma m1 is less than sigma m4. So if you applied a much higher stress level, sorry, I mean in this case, sigma m1, the higher stress will lead to faster failures in fatigue conditions. That's what you can see here. Okay. So sigma m2 is greater than sigma m1. So you can see that um, if you apply the higher stress, this, I mean, if you dropped it down, the number of cycles, um, it will fail much faster, essentially. Okay. Now, there are a couple of different ways in which you can figure out the fatigue life. So, what is the safe stress level that you can apply? So, there are multiple relationships that you can apply. So, the most common one is called the Goodman relationship. So, if you know the fatigue, safe fatigue stress, and if you know the mean stress level, and if you know the tensile strength, so sigma A is the fatigue strength in terms of the stress amplitude, where sigma m is not equal to 0. Sigma m is the mean stress. So that is the fatigue strength, and so if the mean stress were to be 0, then you have a certain fatigue strength. So if you apply a certain stress level, um, you can calculate the fatigue strength and this is called the Goodman relationship. So most of the time we will be using the Goodman relationship. So there are also other variations of that. One is called the Gerber relationship, the other one is called the Soderbergh relationship. So depending upon what your organization or your company is using, you should use that particular type of relationship. So you will be using that. So here is an example. So the endurance limit is typically the uh, sigma fat, sigma FAT, or sigma fatigue. So that is the endurance strength. Okay. So the tensile strength is 1400 megapascals. So would you expect failure if component is subjected to repeated loading from 0 to 600 megapascals? So alternating stress means mean stress is equal to 300 megapascals. So uh, and no failure expected using the Goodman relationship. So if you put these numbers into the Goodman relationship, you will find that uh, it can easily withstand more than 600 megapascals. So which means that the component is not going to fail. But if the component has a residual tensile stress of 700 megapascals, um, then you may see that it is unsafe to use the component in within that. So you have to probably add that to the so your mean stress will actually go up to 1000 megapascals. So which means that it may not withstand the that kind of a stress level. Now there is also something. Suppose you apply different stress levels and you want to calculate the total lifetime. So you applied a stress and you had so many number of cycles at that stress level. Then you change the stress and then you applied so many number of cycles. So you want to calculate the total lifetime. So if you know the N1, Ni at a particular stress level, a particular number of cycles at sigma I, and if you have um, combined relationship, so you have a summation that you can use, and with the understanding that um, summation of that should be equal to 1. So from that you can actually calculate the number of cycles at each stress level. So here is an example. So a traffic bridge has been in service for 3 years and carries a large number of trains, trucks and automobiles. So we need to determine the remaining lifetime. So if you know that for automobiles only, you have a fatigue lifetime of 10 to the power 8 with a loading rate of 5,000 vehicles per day. Then you have trucks, 2 into 10 to the power 6 at 100 vehicles per day. And if you had 10 to the power 5 lifetime with 30 trains uh, going going like that. So first calculate the damage. So what is the total damage over 3 years? So 1095 is 365 into 3. So 1095 times 5000 by 10 to the power 8 plus 100 over 2 into 10 to the power 6 plus 30 into over 10 to the power 5. You calculate that equal to 0.438. So if you are going to be carrying only trucks and automobiles and no trains at all, then you can calculate um, the remaining lifetime. So D is the number of days that you want to calculate it for. That is equal to 0.562 So from that you can calculate the number of days that it will withstand. Okay. So one of the big issues that you might find that you have to uh, look for is the effect of notches. And effect of notches could be substantial in some cases. So from these set of curves, you can see that the fatigue lifetime can change um, or decrease drastically with respect to normal polished specimens and then severely notched specimens. So severely notched specimens will have much lower fatigue limit than compared to normal polished samples. So you have a relationship that you can use. I mean, here is a typical relationship that you can use. So for different materials you have notch sensitivity factors, so which can range from 0 to 1. So if the material is not sensitive at all, then q equal to q will be equal to uh, I think it is equal to, should be equal to 1, I guess. um, so if you are given that value, I mean, and if you are given these curves, you should be able to calculate um, the effect of the stress concentration factor and the radius of the notch root. Then you can calculate the notch sensitivity factor or vice versa. Now, if you had a notch, typical notch, and then if there is a fatigue crack that is being generated in the sample as a result of that fatigue crack, pre-existing fatigue crack, how will you measure that? One of the typical ways to monitor that is by non-destructive evaluation. So that is a very typical thing that you do, especially in the aerospace industry, aerospace, automotive industries, etc. You can, automotive is much less, but definitely in the aerospace industry, you want to measure the uh, cracks, inside cracks through non-destructive evaluation. So what is the difference between a smooth sample and um, a rough sample? There is typically no size effect in axial loading of smooth bars, but there is a size effect in smooth and notched bars in bending. And you will also find that there is a size effect in uh, axial loading of notch bars. So this is, if you have a larger sample, then it will fail much faster. And the reason is that if you had a larger sample, there is a higher probability of finding a weak area in that larger sample. Okay, so um, if you have a smooth sample, then there is no size effect, whether it is a small sample or a big sample. But if it is a if the sample is in bending, then there is a size effect in whether it is smooth or notched. If there is notch bar, then there is a size effect in axial loading of notch bars. So that means if you take a larger sample, it will fail um, much faster than a traditional, I mean, than uh, non-notched sample. So what is it that you can see the effect of material composition? So most steel alloys have a clear fatigue limit, and the fatigue limit is a clear hockey stick if it is a BCC type of structure. If it is FCC type of structure, or if you add say nickel or any kind of austenitic stabilizing elements, then you will find that it does not have a clear fatigue limit. And typically what you will find is that, especially for steels, the fatigue ratio is between 0.35 to zero point 0.6, between fatigue uh, stress to the tensile stress. So that means if you typically apply a maximum of 10% of the tensile strength, 10 to 20% of the tensile strength, you are in a safe stress level. But if you start going up to 30, 35, 40%, then you are playing with fire. Non-ferrous metals do not have a very clear fatigue limit, and typically this is usually defined as 10 to the power 7 cycles, or um, 10 million cycles. So what is a magic number? Magic number is 1 million cycles. So typically for steels, um, it can be, so that's what we said, it can be between 0.35 to zero point 0.6. I mean, for non-ferrous also there is a fatigue ratio of fatigue stress to tensile strength of between 0.35 to zero point 0.5. So if you plot it between that, you are in a safe zone. So if you look at the handbooks, it will say, what is the endurance limit? Endurance limit is the maximum fatigue stress level that you can apply safely and get away with. So how can you improve the fatigue strength of materials? These are typically done by either by mechanical treatment or by thermal treatment. So mechanical treatment is, there is something called shot peening. You take these materials and you shoot or bombard them with, uh, it used to be small lead balls, but nowadays it is made out of small steel balls. And when they hit the surface of that material, it applies some kind of a compressive stress on the surface. So when you have that compressive stress, what happens? When you apply a tensile strength, it has to overcome that compressive stress before it will start applying the tensile stress. So that means by doing short peening, you are increasing the fatigue life of your component. The other methods are cold rolling or grinding or polishing. So typically polishing and grinding can improve the fatigue life of a component. There are also thermal treatments. Typically, if you do flame induction hardening, so if you have a rotating component like a tappet rod in the automotive engines and things like that, they harden them by flame or induction hardening. That can improve the fatigue life of the component. You can also do coatings, or you can do case hardening or nitriding, or you apply some kind of a plating that can improve the fatigue life of your component. So if I ask you in the test, what are the methods by which you can improve the fatigue life of your component, you should please be able to say that. Okay, so please remember that. So what you will also see is that the microstructures are very different. So if you have a carburized layer, um, you will find that it can improve the fatigue life of your component. But if there is some kind of a decarburization or oxidation taking place, it can reduce the fatigue life of your component. The other thing that you could do is you can apply some kind of a pre-stress or surface treatment of the threaded bolts. So if um, you can see that if you take unground stock and you do additional heat treatment, it has got a very low fatigue strength. But suppose you take ground stock and you put threads on them with no subsequent heat treatment, it has got much better fatigue strength. Polymers typically um, can fail due to fatigue failure. So due to fatigue failure, um, there could be some local heating taking place, and that can lead to cyclic thermal softening and improved fatigue life. But suppose it is only true fatigue, it can break in a catastrophic manner for polymers. So it's typically um, it's a very complicated behavior for polymers and fatigue. Okay, so that's all you need to know. In the case of composites, um, there can be differences due to notch and unnotched samples also, but it is much less pronounced compared to metals. So here are some pictures of the samples, etc. What are the different kinds of stresses that you can apply and how that can apply the fatigue life, etc. Okay, so you can. Here are some examples. I'm just giving those to you. That's all. Okay. So I think that's all I have. So here are some typical samples. Uh, and one thing I want to show is this. If you can pre-stress the bolt and it can change the, um, so you are applying some kind of a compressive stress uh, due to the preloading, and it can improve the mean fatigue lifetime. So for example, if you apply a very large preload of uh, 8,420 pounds, the mean life fatigue lifetime goes up from 6,000 to 5 million cycles. Okay, so that's all I have, and let me know if you have any questions. Please email them to me. Okay. don't know where that is.